Hello everyone, and thank you for inviting me to the Machine Learning and Friends Lunch at University of Massachusetts Amherst. Today I'm going to talk about learning robotic pick place with uncertain object shapes. As an introduction, these are my colleagues in the robotics computer science area at Northeastern. On the left is Robert Platt's lab, and in the middle is Chris Amato's lab, and on the right is Lawson's lab. Okay, so here's a clip from a video of our latest robot experiments. I posted this on Facebook to see how non-robotics people would react to this. And the things they thought it might be used for in the future is, can it be set up to pick toys after kids go to bed? And can the robot arm help to change a baby's diaper? Or can it be combined with a vacuum robot to clean and pick up toys? So there seems to be a common thread of picking up toys here. But perhaps a good question to ask is, why isn't there a robot that can do these things now? So here are some other applications from our lab. The first two on the left is a scooter to help people that have trouble moving around on their own. So the system, someone uses a laser pointer to indicate what object they would like to pick up, and the robot will retrieve the object. And the newer system can even place the object. And then over on the right, we have a system that can be used for litter removal. So in each of these cases, these are so-called open world environments in the sense that the objects that the robot will encounter are going to all be unexpected or new. We might have some idea of the kinds of objects the robot might manipulate, but we don't know what objects exactly. So how can machine learning be used to help with this problem? So in this figure on the bottom, typically, well, oftentimes in robotics, the sensor data we get is point clouds. And this is just a list of points. And this can come from a depth sensor or from a range sensor. And the robot needs to know, how do I grasp it? And where can I place it tightly in a filled box, for instance? In order to answer these questions, the robot needs to know more about the geometry of the object. So I can think of two ways of getting more information about the object. One is to get multiple views of the object and to fuse those observations into one geometry. But that might not always be possible. The robot might not be able to reach, for instance, if the object is in a shelf, it might not be able to reach all the way around it, or it might take a lot more time than you would like to scan the object. The other option is to guess the object's properties from past experience. So this is what it looks like. So we used some network to predict the complete shape of the object and also the uncertainty in the completion. So the yellow means it's very confident in the prediction, and blue or green means it's less confident. And this is what the ground truth point cloud looks like. So machine learning can be used to predict the object's properties, for instance, its shape, from past experience. Okay, so I want to talk somewhat more formally about the specific problem that I've been thinking about, which is called rearrangement of unknown objects. Okay, so this is the abstract system that I'm thinking about. We have a robot. It has an end effector which can open or close, or it could be a vacuum gripper, for instance. It could turn on or off to release the object. And observations are point clouds acquired from depth sensors, and we're going to assume rigid objects just to keep things simple for now. So the rearrangement of unknown objects problem is, given a move binary effect system, the system on the previous page, and a set of goal arrangements, where a goal arrangement specifies a pose for each object, find a minimum number of actions that moves the objects to a goal arrangement. For example, the objects might initially appear in some configuration, and we might want to stack them linearly. Now, what does pick and place have to do with this? So pick and place is where we constrain the problem somewhat in order to simplify it. So the actions we're going to take are going to fix the object in the gripper, and when we release the object, we hope that it will rest stably. So for instance, we're not pushing, we're not sliding, we're not throwing the object around, and we're not swinging it in the hand. Okay, so as an example of a goal arrangement, or actually a set of goal arrangements, it could be an infinite set, so we need to describe it by a Boolean property. For example, each bottle must be placed upright on a separate coaster. Okay, so this rearrangement problem has several challenges. In general, even the fully observed problem, where we don't get point clouds, but we actually know the shapes and the positions of the objects, even that version is p-space hard. And perhaps that's just because the way we formulated the problem is very general. The proofs for p-space hardness often involve these very complicated puzzles for the robot to solve. But even if we're not solving a complicated puzzle, we have to deal with the partial observability. And so we could formulate this as a POMDP with, which has continuous observations and continuous actions, and very high dimensional observations. And so we can basically, we're not really looking at exact solutions here. We're looking for approximate solutions. Okay, so there have been two main approaches. Historically speaking, and also the second approach that I'll talk about today is a modularized approach. So on the one side, we have a perceptual component where the sensor data goes in and we predict what the geometry is going to be like. And usually this is handled with some machine learning technology. Now on the other side, we have a planner or a controller that will take that geometry and produce actions. This has some advantages. First of all, different communities can independently develop perception and control. And then parts of the system could be reused for different tasks. One challenge with this, though, is that independently designed perception and control can be suboptimal. And to think about why this might be the case, suppose that the robot doesn't see part of the workspace at all, but in its experience, it believes there are normally objects there. So it predicts objects there, but it's very uncertain about their shapes or their exact positions. If the controller or the planner is not aware of that uncertainty, it could try to manipulate those objects, and it will almost certainly fail. Okay, so the second approach is to forget about having separate perception and control modules and just to have one module called a policy. And in this case, we get a point cloud as input and actions are the output. The advantages of this approach is that integrated perception and control is a given. So everything is integrated. It's also, the algorithms are also quite general in this method. There's very little task-specific hand coding that you need to do for the algorithm itself. But of course, it comes with its own challenges, which learning takes a long time, and the policy can be brittle to changes outside of the environment in which it was trained. So today I'm going to talk about two different approaches that we have taken to this problem. One is learning a policy. The first one is learning a policy using deep RL, And the second one is to use shape completion, and that's a more modularized approach. So this is the first approach, using deep reinforcement learning. So the problem considered here is very similar to the problem introduced in the introduction. The only difference is that the robot arm is not being considered. We're only considering as actions the position and orientation of the effector. Otherwise, everything else is the same. And we want to learn 6-off pick and place. So, most people faced with this problem will use either an actor-critic method or policy search or policy gradient, because the actions are in a high-dimensional continuous space. But here we're going to do something different. We're going to learn a value function. And of course this is going to be challenging largely because of the action space, but also the observations. Okay, but we're going to make a couple of observations that will make this easier. First of all, a large area, the whole robot's workspace, is being observed in detail. And that's not really necessary. The only part we need to see in detail is the part that we're going to grasp, or the part we're going to place. And the rest of it is just, it doesn't need to be seen in that much detail. Okay, so yeah, the idea is to attend to part of it in low resolution. And then actions. So actions require many samples. We're in a very high dimensional space. So what we're going to do is we're going to decide actions in stages. So you don't need to necessarily decide X, Y, and Z all at once. You could decide X, Y, and Z, for example. Okay, but it's easier to illustrate this idea with an example in a simple finite domain. Okay, so this is the grid world, and the goal is to place this red triangle onto this blue circle. The state is peg positions, disk positions, and a holding bit, telling you whether or not you're holding a peg. And there can be multiple objects. There can be multiple pegs and multiple disks. And actions are a grasp place for every location in the grid. And then there is some reward that's appropriate for this task. Okay, so what we're going to do is we're going to reduce the observation first of all. Instead of seeing the entire grid in detail, it only sees 8 cells at a time. And each of these 8 cells tells you occupancy information. Is there a peg here? Is there a disk here? In the actions, there's also only going to be 8 actions, and that's to select which cell you want to zoom into. So this dramatically reduces the state and action spaces. Okay, so this is what this looks like through time. So the yellow region here is the area that the robot observes, but it observes it only coarsely. It only sees 8 cells at a time. And the green area is where the robot chooses to act next. Okay, so it decides to zoom into the front bottom left, and then it's over here, and now it only sees this area, and everything outside the yellow region is ignored. It next selects the triangle, and then it zooms into there, and now everything outside is being ignored. And then when it goes to place the object, it repeats the process for the disk. Okay, so there are some benefits to using HSA, which is hierarchical spatial attention. So first of all, in this grid world case, the size of the action space is now 8 instead of m cubed, where m is the length, width, and height of the grid. So the action space is much smaller. And the observation space also becomes much smaller. So I should point out here that this is, we're thinking about finite horizon problem. So that's why we have time is included in the size of the state space. And also log 2 of m is included in the size, because when we make this abstraction, we need to do log 2 of m times more actions. So some constant times log 2 of m times the maximum number of time steps. So it's a great reduction, but of course, there's no free lunch, and what is the disadvantage to doing this? Well, HSA introduces partial observability into the problem. In other words, the Markov property is not preserved. But for some problems, this may be a big deal. For some problems, it may not be. For instance, for the grid world, you can use something called Q-star irrelevance to show that Q learning will learn an optimal policy anyway. Okay, so here's a comparison between different abstractions in the same grid world that I was talking about. Here there are 3 pegs and 3 disks, and the size of the grid is 16 by 16 by 16. So in this case, without any abstraction, just using a standard the standard MDP, you'll quickly run out of memory. The system will just quickly run out of memory. However, these are 3 different abstractions. The blue one is the HSA version that I was talking about. And then there's a slightly modified version that does much better for this grid world task. And what does best, though, is something called deictic image mapping, which it only looks at one cell at a time in terms of episodes. But in terms of wall clock time, actually this red line, the look ahead HSA, is much faster because it doesn't need to evaluate m-cubed actions. Okay, so we tried this also in continuous domain. So here's a pegs on disk domain. So basically 1 level HSA is equivalent to DQN. So we compared that to a 2 level versus a 3 level HSA, and this is in a the action space is 3-dimensional here, 3-dimensional continuous. So it can choose X, Y, and Z. And what we see is that it looks like the 1 level learns a bit faster, but in the end, they all do about the same, basically the same at the end. So this is good because the 1 level has to evaluate many actions, and actually in terms of wall clock time, it runs much slower than 2 or 3 levels. And if we go higher than 3 dimensions, it's not even possible to compare to 1 level because you'll run out of memory or time trying to sample all of these actions. Okay, so this is what this looks like implemented on a physical system. So we're looking at placing bottles on the coasters, and we're going to first look at a 4-dimensional problem, so X, Y, Z, and orientation of the gripper. So these 4 figures on the bottom are showing 4 different levels of HSA. So in the first level, this is what the robot sees, and it samples actions pretty sparsely. So in a 3-dimensional world here, it samples about 125 actions, and it can evaluate that pretty efficiently on the GPU. But still, it's not fine enough to do fine hand positioning for grasping. So the next step is zooms in, and it samples within a smaller region that it previously selected. Okay, and then the next stage, it zooms even further in, and now it's deciding position at a millimeter scale. And at the last stage, it will select orientation. And if you want to make this a 6-DOF problem, you just add 2 more levels of orientation. Okay, so here are some learning curves for that. The one on the left or the blue line on the top picture is the number of objects grasped, so it does pretty well at grasping. And then the red curve is showing how many times it placed a bottle upright on the coaster and it didn't fall over. Okay, and we also compare with distractors and without distractors. And in this case, it does about the same, but you have to retrain the system once you include distractors. Otherwise, it doesn't do as well. Okay, and we did some real robot experiments. We were able to implement this on a UR5 system, and the grasp success rate is really high, like around 98%, using this hierarchical attention method. The place success rate is a bit lower. It does about 90%. A lot of times it gets the bottles upside down or it places them too high. This is what this looks. We tried this on some 6-off problems as well, but only 2-step problems because training for the 6-off case takes a bit longer. So stacking blocks and placing the mugs upright and moving the bottle on the coaster. Okay, so there's some work related to this. Previously, we did something. We also used reinforcement learning to do pick and place problems, but in this case, we addressed the action sampling complexity by combining with supervised learning. So there was a component for training a grasp detector that would give us a discrete set of grasp choices. And you could imagine doing the same thing with a place detector. You could detect places. And the reinforcement learning would decide those as actions. Okay, so there was also a good related project by Peter Allen's group. And here they have even more degrees of freedom. They have a 3-fingered hand they're controlling. But they're operating in this space of the depth image, not the point cloud. And Dion and Colin and Rob were working on this project. And they have some comparison to, well, they made some changes to get better results, and they made some comparison to policy search methods, or actor credit methods like DDPG. Okay, but of course, this idea has a lot of limitations. Training takes a long time, but perhaps what's more frustrating than that is for these cases where you need to use function approximation, performance never really is perfect. And so you can't just run it for a long time and be sure that when it's done that it will be running perfectly at the end, even for simple tasks. And it's also brittle to changes in the task or environment. Okay, so that motivates looking into the second approach. So this is a modular approach. We're going to use shape completion. Okay, so looking back at the picture we saw earlier, there's a lot of people separately working on perception and control. And there's a lot of really good work in both areas. But these problems are being analyzed independently. And the question is, can we adapt these components to account for perceptual uncertainty so that they work better together? And what we're going to do something very straightforward. We're going to modify the perception to produce an estimate of its own uncertainty. And we're also going to treat uncertain actions as a planning cost in the control module. Okay, here's an overview of the system that we have been studying. So we have an environment which has the objects, it has the robot, and it produces a point cloud. And after that, we do object instance segmentation. And for each of the objects that it finds, we do shape completion. In each of these modules is going to predict some uncertainty about its perception. That's going to go into a 3-level planner. So the first level, it does arrangement planning. So it's going to consider how does it displace the objects without consideration to the robot arm or even the end effector. And it will give multiple solutions to that so that the Regrasp Planner will hopefully find one that's feasible. And so the Regrasp Planner is similar to the HSA project in that we're only looking at the gripper here. And it plans grasps in places. It plans a sequence of grasps in places to move the object to one of the goal displacements. And then after that, we're going to use motion planning, standard motion planning algorithms to connect the grasps and the places. And then the process repeats. So we execute the first pick place, and then the process repeats, similar to MPC. Okay, so what we're going to do is we're going to incorporate uncertainty into the Regrasp planning cost. So we're going to mainly focus on the Regrasp planner. But first I will mention a little bit about the object instance segmentation. So here we're going from point clouds to point clouds. So we're using BowNet to do this, which has a PointNet backbone, and has a lot of other interesting things going on in there. But mainly what I want to focus on is the output. So the output's a n by k matrix, where k is the maximum number of objects that you could segment, and n is the number of points in the point cloud. And so each row is a distribution over segmentations for that particular point. So the row-wise max is going to be used for uncertainty estimates. So it's basically estimating the probability the segmentation is correct. Okay, the colors, here's a segmentation of 6 objects. The colors here represent the uncertainty. So yellow is very confident, and blue it's less confident. So here it's less confident because it's close to this object. And you can even see on one object, for instance, this blue bottle is confident when it's far away from the car, but closer to the car it's less confident in the segmentation. Okay, so for shape completion we use something called PCN, or Point Completion Network. And actually we modified it a little bit. So in goes the point cloud, and there's an encoder, which is something like PointNet. And then there's a decoder, which is several inner product layers. And out comes the completed point cloud. Okay, but we added another part to the network, which is an uncertainty decoder, which has the same architecture as the point decoder, except it has just in outputs, and it's trained with a binary cross entropy loss to predict the probability. Well, it estimates the probability the nearest ground truth point is less than Euclidean distance beta. So in other words, is for each point, what's the likelihood, or what's the probability that the point is near a ground truth point? Okay, so this is what shape completion looks like. So these are novel objects, but they're from the same category that it was trained with. There were several, 7 or 8 training categories. So this is what the input point cloud looks like on the top row, and the completion is here. Yellow means it's pretty confident, and then the blue is less confident. So for instance, on the mug it's less confident in the handle. On the dinosaur it's less confident in the legs. Okay, so just to remind you, we're going to incorporate this uncertainty into the Regrasp Planner's cost function. So I'm going to digress a little bit and describe what is regrasping and why do you need it. So this picture comes from Tornason, Lozano Perez, and Mazur in 1987. Basically, regrasps are needed due to kinematic constraints. If you think about the grasps on the object at the start configuration, all of those grasps might be in collision at the place you plan to put the object. And if that's the case, you need to do some number of regrasps. So like in the second and third pictures, it will place the object in some temporary location and then grasp it again in a different place that it wouldn't have been able to grasp from in the initial configuration. Okay, so our Regrasp Planner is similar to Tornason and others. And so in goes the complete point cloud. And we also get the per point uncertainties, U. And we also get some goal poses and costs. So we get multiple goal poses and costs per object. And so T represents a goal pose and C is a cost. And you might want to attach a cost to a goal pose because for some task specific reason, some goals may be more preferable than others. And we're going to run this algorithm in parallel for each of the completed objects. And at the end, the one with the lowest cost will be taken. So for some number of steps, or you could run it until a time limit is reached, it's going to sample more grasps. It's going to sample temporary placements, and it's also going to get grasp costs and placement costs. So a temporary placement just means it's a non-goal placement. And then it puts us into a regrasp graph, which regrasp graph is just telling you it's a matrix of grasp and place combinations. And if the grasp is not reachable at a particular combination, then the cost for that entry, or that entry in the matrix, is infinite. Otherwise, you just sum the grasp and place costs. And then you can use A star to find an optimal plan given your current sampling. Okay, so let's talk about the cost function that's being used by A star in this case. So this is the general form of the cost function that we use. There are 4 terms, and W1 through W4 are trade-off parameters. So you can set the relative importance of these different terms. So the first one, M, is the length of the pick place plan, or the number of picks and places. And typically this is, in the planning literature, this is mainly what is used as the cost. You just want to minimize the number of regrasps. Okay, and skipping the middle one for a second, the last one is a goal cost. So depending on which goal pose the Regrasp Planner chose, you might incur a different penalty. Okay, so the middle term is what's interesting. This is where uncertainty comes in. So what we want to do is we want to maximize the probability that each grasp in each place is successful. And in pick and place, successful means that the object is rigidly in the gripper for a grasp, and then when you place it, it's a stable placement. So making some independence assumptions and or making an independence assumption, we get a sum of logs. So it ends up being a sum of positive terms, which is very convenient for planning with A star. Okay, so GI is the probability that the grasp is antipodal, or in other words, antipodal is technical conditions for a 2-finger gripper. That it's, if you can make those conditions, then it will be fixed in the hand. So PI is the probability that the place is stable. Okay, so the question is now how to estimate GI and PI. So we look at several different ways of estimating GI and PI. Okay, so the first way, it's not really a new idea, it's just we're putting it into our probabilistic framework, is to estimate the quality of the grasp. So one way of doing this for antipodal grasps, well, let me first define what an antipodal grasp is using this picture. So here's the left finger and the right finger. And then these fingers will make contact with the object at some points. And then we draw a line through those contacts. And then we also have the friction cone at those contact points, which the orientation of the friction cone is determined by the surface normals on the object. And the width of the friction cone is determined by the coefficient of friction. So the antipodal condition is just that the line connecting the contacts, or this red line, it has to be in both friction cones, which it is in this case, in this picture. However, if we're uncertain about the object shape, we may be inclined to not want this red line to be close to the edge of the friction cone, because if there's a slight error in the shape, it might not be an antipodal grasp. So that's the intuition behind the grasp quality metric that we're using here. But we put this into our probabilistic framework. The second approach we can look at is Monte Carlo sampling. So what we could do is we could sample segmentations completions, or sample shape completions. And there are different ways you could do this. One is using dropout on the shape completion and segmentation networks. And Lundell does something like this for uncertain grasping. Another thing you could do is use a VAE. So far I haven't seen anyone try that. Or you could use the pointwise uncertainty estimates that I was talking about earlier. So we use this one for comparison to the next method. And this is what it looks like. So since it's a pointwise uncertainty estimate, the Monte Carlo samples are going to be a bit noisy. So this is what this looks like for 6 objects. And here's one sample, the second sample, the next one, next one, next one. And typically we'll sample something like 50 of these. Just go through it again. And you'll kind of notice that the green bottle is more stable than the other objects. So what's going to happen is the cost for the grasp in places for the green bottle are going to be less than for the other objects. Okay, so another thing we could do is look at the uncertainty at the contact points. So for the grasp, there are at least 2 contact points with a parallel jaw gripper. And we can look at the uncertainty values. We can somehow combine the uncertainties for the segmentation and shape completion, which is what's being shown in this picture. And yeah, the grasp will just receive a penalty if it's touching uncertain areas. And we put this into the probabilistic framework, so it's estimating the probability that the grasp will fail or succeed, or we're modeling that using the contact points. Okay, so a fourth approach is called success prediction. And the idea here is simply to use separate neural networks to predict whether or not the grasp is going to be antipodal and whether or not the place is going to be stable. So when doing that, an important thing to consider is how to represent the grasp and how to represent the place to the neural network so that it generalizes well. So what we do for the grasp is we only look at the points inside the hand, and we transform those points into the hand reference frame. So the points are relative to the hand frame, not the world frame, which is somewhat arbitrary. And for the places, we do something similar. So we take the points for the completed shape for the whole object, and we transform them to the pose where it would be if it were placed, and then we center it. We put the origin at the bottom center of the object, and that's the descriptor for the place. And this actually works pretty well. And again, we use PCN to do the prediction. So the point cloud goes in, and then we have the encoder and the decoder. This time it only has one output, which is GI or PI, and it has a sigmoid activation, and it's trained with binary cross-entropy loss. Okay, so evaluation, we evaluate this on 3 different tasks. So the first task is to arrange blocks from tallest to shortest according to the longest edge, like it's showing in the sequence here. And at the end, it's reached a goal. And the second task is to place bottles on coasters, like we did with the HSA project. And the third task is more challenging. So the third task is we're given objects from multiple categories, and we want to pack them into a bin. And we want to minimize the height of the final packing. So in this case, the space in the bin is pretty confined, so we may need to do several regrasps. Okay, so here is the perception ablation study. What this is doing is it's evaluating object instance segmentation and shape completion in terms of pick place performance. So we first look at, in the first column, we see ground truth, segmentation, and completion, and it does about 93% successful in placing the objects into the bin. So this is with packing. Then once we go to imperfect shape completion, this drops down to about 75%. And this is in simulation, by the way. And then once we take out shape completion, or once shape completion becomes error prone, it drops to 71%. And then if we use ground truth segmentation, but we don't use shape completion at all, the system is essentially crippled because the planner relies on having the complete geometry, and without that, it can't find grasps. So a lot of the plans just fail. Okay, so this is a comparison of the different ways of estimating probability of grasps is successful, or the probability place is successful. And we compare that to two baselines. The first baseline is no cost, so just take the first plan found. And the second is the step cost, so this is what was traditionally used the most often. So minimize the number of grasps. And then we have the GQ method, and then the Monte Carlo method. And these things are not, you can have combinations. You can combine the MC and GQ methods. There's no reason not to. And there's also the success prediction and contact uncertainty. It turns out with bin packing, the same category novel objects, GQ plus MC does the best for grasping, and for placing stably, SP does the best. And the bottom table is for novel category objects. So here the perception is very error prone. And so the GQ plus MC achieves the highest place stability rate, but SP does better for the grasping and overall. Okay, and here's another task. This uses the same objects as the bin packing task, but for each episode, it's just take one of the 5 objects and place it into some canonical pose. And we did this because it gave there's less goal poses available, so it needs to do more regrasping. And interestingly, it turned out in this case that the SP method did much better than the other methods. And basically, they all do better than the 2 baselines. Okay, so this is showing the complete video that I started earlier. It's going to show a bin packing sequence. And okay, so there it goes. It's going to grab the dinosaur first. Another good thing about doing shape completion is that you can use it for collision avoidance. So when it does the motion planning, you can use the completed shapes like it just did there with the mug, and it's able to avoid obstacles much better than if you only got one view from the sensor. Okay, so it's showing the regrasp plan there and the completed objects, and it's going to continue. So while it's continuing to pack the bin, I'll talk about the results of the experiments for the bin packing and also bottles on the real robot. So we compared the step cost versus the MC cost. With the step cost, we get about 87% success. And with the MC cost, we get about 91% success, actually putting the objects into the bin. So the MC method does about 4% better. And occasionally we do need to do regrasps. The step cost case does 11, MC cost does about 14 overall. Let's see. For the bottles, we use the step cost here, but we compared to hierarchical spatial attention. And it turns out the shape completion method is doing better. We even used more challenging bottles. We used bottles that were harder to distinguish in orientation and that were wider. It's going to show the bottles next in the video. That's what the final packing looks like, and then it's going to show the bottle arrangement. But it turns out the shape completion does slightly worse in the grasp success rate, but that's purely because the objects are harder. All the failures were on the more difficult objects, and the play success rate is really good with the shape completion method. It does perfectly. which is interesting because it has to get the orientation of the bottle right, and it can't place it too high or too low, or else it'll fail. Okay, here's showing, in the video, it's showing a regrasp that it needs to do for the blocks case, because it thought this blue block was the tallest one, so it needed to grab it first, and it wasn't able to reach it in one grasp. Okay, so I'm going to skip the rest of the video. Work related to this, probably the first work to consider non-trivial placements with novel objects was Jiang and others. And they did something similar to what I'm calling the SP approach. So they have a neural network that predicts the probability that or it gives a score. It gives a score that the object is going to be stable and meet some human preference criteria. So the next related project was Manueli, Gao, Florence, and Tedrick. And they use a very sparse representation of the object when they're planning. So they're using key points. And they do really well at pick and place of novel objects in the same category. But what they don't consider is regrasping, and they don't consider uncertainty, perceptual uncertainty. And very recently, one came out by Mitash, Shomwen, Bolaris, and Bekris. Here what they do is they're trying to put the object into a narrow slot. And they're conservatively assuming that the object is as big as the unobserved region. So in order for it to fit in the slot, they need to scan the object from different views in order to fit it into the slot, in order to reduce the uncertainty. Okay, so this method also has some limitations. We need better stopping criteria for the grasp place sampling. The uncertainty aware cost functions take longer because you can keep sampling and sampling, and the cost goes down and down, and you don't really know when you should stop. Another thing is it doesn't yet incorporate active sensing. So how to do this systematically without incurring a great computational cost. Okay, I would like to acknowledge Rob, Andreas, Lawson, Yuchen, Chris, and David for helpful feedback and discussion on these projects. So that's the end. Thank you for listening.